So today we're going to look at the SIP study guide that you may or may not have picked up. So we're going to go through half of this. So for number one, we have a graph that says dog data, and then the mass in kilograms, and then the years ranging from year 2000 to 2004. So generally, if you are doing a graph that's over time, it will be a line graph. So here it asks what's the independent variable. The independent variable always goes on the x-axis, which is here. I remember this as if you have an ex-boyfriend or an ex-girlfriend that makes you independent. And this is my x-axis, so my independent variable is the year. The dependent variable is my y-axis, which is here, and its mass in kilograms. Write a hypothesis. Based on the notes that we took earlier this year, the hypothesis would be an if-then statement plugging in your independent and dependent variable. So the hypothesis could be if the year, let's say years progress, the dog, oh, I ran out of room. The dog, I'm going to finish it down here. The dog will be heavier. In this case, it started that way. The dog gained weight, but then it plateaus and it decreases. So does the relationship between my independent variable and dependent variable, does it remain the same? No, because it plateaus between 2002 and 2003, then it decreases. Does the relationship remain the same? If it stayed the same, it would have increased as the years went on. Okay, let's look at number two. So here we're looking at incoming solar radiation, and it's broken down into three categories. The first one is reflected by the atmosphere, the second is absorbed by the atmosphere, and the third is absorbed by the Earth's surface. Now it says complete a pie chart that uses the above data. And I know that I'm always going to use a pie chart if I am looking at percentages. I also know that a pie chart is one way that I can show qualitative data. So what it's asking me to do is divide this into different sections. Well, I know if I'm looking at a circle, I will have 50% would be this part. So this I could label it, or I could color code it, or I could hashtag code it. But this is, I'm going to go ahead and write absorbed by Earth's surface. And that shows half, which is 50%. So now I have this other half, and it's not going to be quite 25 and 25, so one has to be slightly larger than the other. So this would be my reflected, and this would be my absorbed by atmosphere. I think that's all I need. Okay, so number three, the effects of NaCl, which I know is salt. The effects of NaCl solute on boiling point. So the solute is what's going to go into the water, the lute. That's not on here, but I just think that's good to remember. So if I look at my grams of NaCl, I see that as they increase, the boiling point decreases. So my independent variable, oh, I don't have an x-axis, but I know the thing that I'm changing that I have control over. I don't have control over the boiling point. I have control over how many grams of NaCl. So my independent variable here is grams of NaCl. The dependent variable is what I'm measuring, and I'm measure that with a thermometer. So that would be my boiling point. So what is the relationship to each other? So as these increase, this decreases. Okay, so as the grams of NaCl increase, the boiling point decreases. Okay, let's look at number 4. Complete a line graph, which I just said goes over time. Complete a line graph using the data above. Show distance and time traveled. So if I look at this, this is my bicycle ride summary, and it's into 4 different sections. And each section is 15 minutes, which gives me a total of 60 minutes. And I've gone a distance, a total of 10 kilometers. So my distance is going to be my y-axis. So this is my distance. And it's in kilometers. And I'm going to do my distance as it goes a total of 10. So 2, 4, 6, 8, 10. That would work. So this would be 0, 2, 4, 6, 8, 10, 12. And then in my time is over 15-minute increments. So here's my 0. I'd have 15, 30, 45, 60. I don't need to go past that. But this is my time, and it's in minutes. So here I go on my bike ride, and in the first 15 minutes, I travel 6 kilometers. Looks like I went pretty fast. And the second part, I don't go at all, but those 15 minutes still have to pass, so I would have a flat line there, because the time is still going on. The next 15 minutes, I travel 3 miles. So there's my 2, and then I go about halfway. Oh, let's see. Actually, I would go by 2, but I need to stay on my 15-minute time frame, so it would look more like this. And then that last 15-minute increment from here to here, I'm just going to go 1 mile. So I would go like that. So I go my extra mile, but it takes me a long time to do it. But when you see a flat line like this, I think it's important to know that I'm not moving. Time continues to move, but I'm stopping. Okay. Let's look at temperature changes over time. Explain how you would find the temperature increased, how much the temperature increased. So if I look at my graph, here I have my temperature in Celsius, and here's my time in minutes. I have a hot cup and a cold cup. So explain how you would find how much the temperature increased. So I would be looking at the cold cup, because it goes from about 22 to about 30. So here I would take my larger number. So I would do my final minus my initial. So in this case it would be, and I'm estimating 30 minus 22, which would give me 8 degrees Celsius. So the second part, how would you explain how you would find how much the temperature decreased. So now I'm looking at my hot cup, which started at 98 and decreased to about 70. So here I would subtract my initial, I would subtract initial from my final. So that would look like I would have 98 minus, let's see, this would be about 70, and that would give me 28 degrees Celsius. Okay, and again, it's a line graph because it's going over time. Okay, let's go to the second page. Okay, here it explains that I'm using a spring scale. A spring scale, which we've not used yet in class, is pulled down toward downward and readings are recorded. So here's my data table. Here's the distance pulled, which would be my independent, and my dependent is the spring scale reading. And so the spring scale reading increases by 2 newtons, which that N stands for, every time I increase it by half a centimeter. So what would the weight be if you pulled it to 0.5? And that's a 0.5, not 5.0. So it would be before this, it would precede it. So I'd be taking a 0.5 centimeters away, and I would be decreasing this by 2, so my answer would be 2 newtons. What would be the height if you pulled it to 3.5? Well, let's see, if I did 3.0, it would be 12 newtons. And if I did 3.5, I'd add another 2, and that would be 14 newtons. When writing a lab report, the conclusion should be based on the data collected. How can you check that your marshmallow data is valid? My marshmallow lab data. Now, I don't know what lab they're talking about, but I know that if I want to validate to make sure that something is good, real, accurate, I would say that I would repeat the lab. Okay, number 8. Here I've got my cardinal population within the state park. Here I have my population, my number of cardinals, and the time in years that's increasing. What are my independent and dependent variables? So my independent is my time. I'm going to write IV is time. And my DV, my dependent variable, is my population. And I can look at this, and as the time goes on, my population increases. As time goes on, population of cardinals increases. Okay, let's move on to number 9. Populations of different organisms in an ecosystem. So here I have the years 1999 and the year 2000. Here the shrubs say 2,352, and the following year they increased. The rabbits went from 908 and increased to 969. Foxes started at 101, increased to 127. And the mountain lions, they decreased. They went from 27 to 19. So what happened to the population of each? All increased except for mountain lions. What conclusion can you make? Well, mountain lions eat foxes and rabbits. So I think that the decrease of mountain lions caused an increase of rabbits and foxes because there was not as many mountain lions to eat the foxes and rabbits. So what conclusion? I would say a decrease of lions led to an increase of rabbits and foxes. Okay, let's look at number 10. Here I have data that starts at 1960 and every 10 years till 1990 talks about the human population in billions and the carbon dioxide levels parts per million. So I can see that as it increases by 250 million, my carbon dioxide numbers increase as well. So by about 7 parts per million. So what is the trend? The trend is as population increases, so, I'm going to continue down here. So does CO2, which I got that from here, CO2 levels. So what should the missing data look like? So the missing data is here. So let's see, if I go from 325, and I had started at 317, I would have 8. So it goes up by 8. Let's see if that trend stays. So if I had 337, which I have from here, in the previous decade I had 325. Oh, it's increasing more. So I'm not exactly sure if that's enough to establish a pattern, but I know that it would increase by about 10 for every 250,000. So if I'm going from 3 to 5, that would be 8. So about 80. I would have this be about 400, maybe 410. So I would say it would be above 400. Okay, and I think we're going to stop there, and you can continue the rest on your own.